And we're rolling, and hopefully have enough storage, and nothing falls over. This seems a little more secure. It does. I know, I've been trying to find like a tripod like that for like an iPad.
Yeah.
Because I just don't like using my phone because it like kills the battery and everything. So. Okay, everybody, if I could have your attention up here. Yes,
I love my hydrofloss in my mouth.
go grab your
You can't do anything without your hydrant.
It's true. Speaking, you just made me thirsty talking about it.
Oh my gosh, now I have to drink water.
I don't even have one.
No, I'm not going to do it. I need to resist.
No, always drink water. That's always what you do. Okay, few announcements here, and then we'll jump into our final lesson before the test and Christmas break and everything else. Okay, so the test. The biggest thing is you need to take the Unit 4 test before you just stop thinking about chemistry. I promise it will be better for you this way. If you're thinking like, oh, I'll study more, you won't. Okay, it's just how it goes. Okay, I know the tricks you play with yourself. You're like, oh, I'll just study longer. No, you don't want to do that over Christmas break. I don't want you to do that over Christmas break. Okay, now, I have left it. Now, okay, first thing, the test is on AP Classroom, not Canvas. Because at the end of the semester and Canvas works as a semester class, I don't know when Canvas shuts down. But I wanted to be able to leave the test open through the weekend so that if you needed to take care of term 2 stuff first, you can, and then take the test. I think, though, I set it to close on Monday or Tuesday of next week on AP Classroom. Okay, if you're all caught up in all your other classes, I would just say it's ready to go. If you need to get things done in this class or other classes for term 2, do that first, and then take the test, okay? But everyone, please take the test through AP Classroom before you go on Christmas break, okay? Now, with that being said, there is a timer on AP Classroom. So it's set up to time you for 30 minutes, but there's a flaw in their system that after the 30 minutes is up, you can still keep working.
Ah, genius.
Don't know what the point of a timer is if it does that.
I have created a timer that intimidates you when you work.
I know.
That's about it.
But you guys make sure when the time stops that you stop working, right? To practice for the end of the year. Okay, for the FRQ, that does work out though where you don't have to try to upload it within the 30 minutes. So you can work the whole 30 minutes of the FRQ and then after the 30 minutes upload it after. Okay? Any questions about the Unit 4 test?
Is it easy?
Easy is a relative term.
That's true. Hard.
Hard is also a relative term.
Is it hard to you?
To me,
Well,
I made it, so no.
Let's see. What's other dumb question? If there was a second grader, how good would he do on the test?
That went through the
Explain to
student.
me.
He's left with
As if
You're
I
saying if
were
you just guess your way through, what grade are you going to get?
probably
30%.
right.
That's what I
Actually,
guess. If you just guessed.
30?
That's failing.
I mean, I know we shift the grade scale for AP, but even 30 isn't what we're shooting for. So,
Yeah, I know. But I got
corrections
directions
on
on
that.
that.
so this test is going on 3rd term, right? Not this term. That's why we're putting on that term. So then after the break, then we'll look at it for corrections, retakes, things like that. Okay. For this term, you do need to make sure you get in all your Unit 4 work. We've only had 1 day of reading, but there is an upload for those notes, so make sure you get those in. And then all the labs, everything is due or closing on Canvas at 10 p.m. on Thursday. Now, with that being said, I am here at school on Friday. So if you're going to use like one of your late passes or something, you can come in on Friday and get help with anything that you need. And I'll still accept it. Or if you want help for the Unit 4 test before you take it, you could come in Friday and get that as well. I'm not here on Thursday. I'm here on Wednesday, but you guys aren't allowed to be here. But you could message me and I can I will be at school all day Wednesday. Other days when you message me, I'm not here at school, so I don't see them as quickly.
Can
But
we just come up to the window and like you open the window or something, or beside you or something?
we just like write on the window.
Yeah.
Here's how you solve the problem.
Truman Show when he writes with soap on his mirror.
Yeah, there you go. What you guys need to do is just because I can't get anything changed, but students and parents get things changed. So we need to find a way next term where they'll let you guys come on Wednesdays. Because I think that would be a very valuable thing. So,
When are you gonna put in like unit 3, like corrections and?
so I'm gonna start going through those today. So if they haven't been put in, they should hopefully by today get put in.
Okay, the quizzes too?
Yes, yep. So all grades, I'm just gonna start getting in. So what I ask is if you're waiting on something you've turned in and it's just not in yet, give me till Thursday before you send me a message that, hey, I turned this in, but it's not graded, because it might just be on my list of like 5 zillion things to grade. But if it's not in by Thursday and you turn something in, send me a message because I make mistakes, okay? The only other thing we are going to turn in today, so don't let me forget before you leave, are your smiley faces. But you're going to earn some during the lesson today, so I don't want to collect them yet. But before you leave, don't let me forget to have you guys turn those in. And then at-home students, send me a picture of your smiley faces if you want to use them. So.
Or just keep them. I mean, I don't know if you can do anything with them, but just, you know.
Oh, that's true. I mean, you don't have to turn them in if you think you're going to be good. So.
But do they not?
What if you don't know if you're?
No, they carry over.
Okay.
Yeah. If you don't know, turn them in. And if I'll put them at the very end. And so like if you're up to an A, then I won't use them. But if you're like, ooh, I might need them, then turn them in today just since it's easier this way. But I won't use them if you don't want me to past a certain point. So.
Do you actually listen to Nirvana, or is that just a shirt?
Any other questions about end of term test or anything else? Yeah.
On the 4.9
Yeah.
assignment, the other ones that aren't like the reduction ones, how do we know what those are? Like, who doesn't classify that?
Yeah, I was actually wondering that too.
For.
Like classifying.
I mean, remind me
Like I noticed one was ionics, but I really was
Asking them which ones are oxidation.
Oh, so they could be precipitation. So how would I identify a precipitation reaction?
If there's a
Yeah, so if you start with two aqueous things and then it becomes a solid. And then the third type we're going to learn about today, which pretty much process of elimination you could know, is acid-base reaction. So those are the 3 types of classifications. So, no, good clarification. Any other questions for now? Okay, pull out your note packet if you don't have it out.
Oh, is there gonna be a new seating chart next term?
Yes.
Wait, can we still sit in the same place?
That's not the
Maybe.
defeats the
Yes.
purpose of a new seating chart.
This is the best seat.
Maybe seating 10.
No, Zach, there's a secret.
Okay, I think I have enough of those.
This one is okay. So this one.
Okay. Okay, let me reset my brain. You have not learned this yet, so let me make sure I forget everything I just taught them to reteach you. Okay, acid-base reactions. 3rd type of reaction that we're learning in this unit. So the first type we learned was precipitation. Next one was redox, and now acid-base. We will have an entire unit dedicated to acids and bases. So this once again is just an introduction. The 2 things you should be able to do in this unit with acid-base reactions are number 1, identify an acid-base reaction, and then label what is an acid and what is a base, and then understand the molecular view of something known as a titration. Okay? So please ask the questions that you have today, but do recognize, like, once again, we'll spend an entire 3 weeks on acids and bases come March. Okay? So first off, what we need to understand, though, is something that goes on at the molecular level when we deal with this thing that we nicknamed the proton like we talked about last time. So all acids and bases deal with this movement of an H plus ion. Now all acid-base reactions are aqueous, meaning they're in water. Because they're in water, this H plus doesn't actually float around as just an H plus. It always latches onto water and makes this substance known as hydronium. So this is its symbol, this is its name, hydronium.
That's a cool name.
It's kind of a cool name. The thing is chemists use these two symbols interchangeably. So whenever I write H plus, everybody, it means H3O plus. It's just the lazy way of writing it. Because this always turns into that, because you're always in water for these reactions. So these mean one and the same. This is the lazy way of writing it. This is the true way of writing it. But you are welcome to show either method.
Everyone can be lazy.
Okay, so just kind of recognize that as we go through this, that it means one and the same. Okay, so all about tracking that movement of the proton or the hydrogen. That's what acid-base reactions are all about. Acids donate their protons, bases accept. So when you're given a chemical reaction and you are trying to figure out the acid and base identity, what we want to look at here is the movement of the hydrogen. So look at the left, look at the right, see where the hydrogen is moving. So on the left of the reaction, I have H with a Cl, and I have H2O. On this side, I have a Cl by itself, and H3O plus, which means, draw an arrow here, that the hydrogen has moved from here to there, which would mean this is my proton donor, which makes it the acid, and water is acting as our base because it has accepted the proton. Okay, so the acid donates, the base accepts. Now in order for this to work, let's look at another reaction here. It's important to recognize that first off, acids are a lot easier, at least first off, to identify because they have to have an H. If it doesn't have an H, there's no way it can be an acid. But it's a one-way definition. Everything with H's aren't acids. So acids have to have H's, but not all H's make them acid. Bases, on the other hand, have to have a site for that H to bond to, or a lone pair. Otherwise, it can't accept it. So to be an acceptor, it has to have a place for that H to connect on to. Okay, so in this case, this would be our acid, and this would be my base. Now what's interesting is, as we noticed, I'm just going to go here so you can get your blanks filled in, is that you always have one of each, right? So the acid and base work together to transfer that proton. The acid loses it, and then the base gains it because it has that non-bonding pair of electrons. With acid and base reactions, how many of you, by raising hand, I don't care if it's yes or no, just be honest here, how many of you are familiar with the pH scale? Raise your hand. Like, I know what it is. Do like this. If you really know what it is, put your hand up high. If you're like, kind of know what it is, or I don't know what it is.
It's like a Google thing, and you identify how acidic and basic things were.
Say that again.
Oh, there
What
was
is
like
this?
there was this Google game, and you like
A
it showed you a tomato.
Google
it's like,
game.
how acidic or basic is this tomato?
Oh, and you tested its pH?
No, you just guessed.
Oh. What's the point of the game? Like, you just try to guess what it is?
I don't know, but it was fun.
Oh, okay, cool. I mean, it sounds like a great game. Okay, you put your hands down now. So, looks like we're all familiar with it. A lot of times you'll talk about sometimes in biology or even like in junior high sciences. So it's a scale set up. Once again, scales are just developed by humans to measure things. And it sorts acids and bases based off the measurement of how much H plus or hydronium is floating around. Acids have a lot of H plus floating around. Bases have very little. Now, the scale seems backwards to that because it's based off a log function, which we'll learn the calculations later. But 1 through 7, or less than 7 on the scale, makes something an acid. Above 7 makes something a base. So 7 is right in the very middle, and that's actually where perfectly distilled water falls. So water isn't technically classified as an acid or a base. How did we label it, though, in these two reactions? Acid and a base.
Water is special.
So by itself, it's not an acid or a base, but it can behave like an acid or like a base. There's other substances that do this as well, and they're known as amphoteric or amphoprotic substances, where they can behave as a base in one case, but an acid in the other. Sometimes they donate and sometimes they accept.
Oh, cool.
Yeah, kind of cool. Water is like, I mean, amazing in a lot of ways, but
Yeah,
another
you
one of the
can
reasons
like
why.
Water's
Water's
I'm gonna write this a little bit more.
There is water.
Yes.
Okay. Sorry guys, it's like my brain
Yeah,
is
that's
gone.
where it says natural flavors.
No, that is the water.
Okay, so when I look at a reaction in what we call the forward direction, okay, in this example, oh, side note, HA is a universally accepted way of saying any acid.
Of course.
So we're not picking a particular one, it's just any acid, right, within it. So A could be anything, but if it's an acid, what is it going to do with its proton or its hydrogen?
It's donated.
Good, so it's going to donate it, so draw your arrow going over, okay? In that process of donating, the thing that's left becomes negatively charged because it's lost a proton.
Sad.
The thing that gained the proton becomes positively charged. Okay, so let's label again. This would be our acid, and this would be our base. Now, something we haven't really covered much is that chemical reactions are rarely often a one-way thing. They often can go backwards the other way. Because all, in a sense, that happens is they're moving around and they bump into each other. And in this process of bumping, this can then give the hydrogen back where it came from. Now, since this substance donated a hydrogen, what could it be classified as?
Acid.
Well, that just is confusing. Now they're both.
So both sides of our reaction have an acid and a base. Now, to help with the confusion, the ones on the product side we call the conjugate pair.
Of course.
So this would be known as the conjugate base,
I'll remember that word next semester.
and this one is known as the conjugate acid. Honestly, the word conjugate is relative to how the reaction is written. In terms of if we wrote it the other direction, we'd call these the conjugates because they're the ones being made. Okay? What we want to do is we're going to practice now identifying conjugate acid-base pairs in an acid-base reaction. Okay, so I'll do this first one, and I'll have you try the next one with your table buddy for a smiley face. Okay? So first step is figure out what's the acid, what's the base, and then we're going to find its corresponding pair on the other side. So track the movement of the proton. So I see that we have HNO2, and now the H is gone. So I've lost, and I always like to draw my arrow to help. The H is moving from here to here, which would classify this substance as my acid, and this substance as my base. Now, the species that remains after it's lost its hydrogen is going to be the conjugate base.
Can we just write C dot? Is that like allowed? Like,
Mm-hmm.
okay, awesome.
That's a real term.
So that's its pair. And then this would be the conjugate acid.
C acid. Sounds like a dumb rapper name.
Yeah.
Acid.
Now, one thing that's important is if a problem says, hey, identify the conjugate pair, be cautious to not call these two things a pair. These are not pairs of one another, right? They're both bases. So it's always an acid with its conjugate base and a base with its conjugate acid. Okay, try this one with your table buddy doing the same thing. Ready, go.
Yeah, so the H2O is base, then the H3 acid.
Oh.
Set your pencil down when you're done.
The second. So I get the first person. The H goes. C acid. No, acid donates. Acid donates.
A base donates.
Wait, I thought acids donate.
Acids don't.
Aha!
So wherever that H is coming from is the acid, and the base is the acceptor.
I learned something. Oh, I wish I could say that.
Okay, check your answer. This should be your base. This is your acid, making this the conjugate acid. That's the conjugate base. Have a smiley face if you got it. Questions so far? This is what primarily everyone you'll be doing on worksheet 4.8 is identifying conjugate pairs.
Yes. 4.82, like, by the end of the term.
Yes. So the Unit 4 test will go on next semester, but all Unit 4 homework should be in by Thursday. Okay, same idea, just looking at it a little differently. Let's identify the conjugate pair given just a species. Okay? So, it's saying these are all acids. We want to identify its corresponding conjugate base. So that means it's giving up its proton. So I'd be left with ClO4 negative. The charge is extremely important to identifying it correctly. Okay? On this one, these are now conjugate, we're looking for the conjugate acid from the base. So this means it's going to accept a proton, so we would get HCN and the charge would go away. Okay, try the remaining 6 with your table buddy for a smiley face.
Smiley face for each one?
Yes.
Whoa, Taylor, you're
Up to
bargaining.
6.
That's one of the stages of that's true. I am your mom. I have come to bargain. Okay, so this bro is like, I just want one. And this one's like, give me one.
This
I mean, that makes sense to me.
Whoa, that's still a minus though. High school, HS minus. That's how I feel about high school. It's sad. It's sad.
Not that bad.
It's sad. Alright, pH 4, pH 3. It has show each three.
I think this one is A2SO. This is 1 minus.
Whoa, whoa, whoa. Let's not drink H2SO4. There's a poem in my head. Tell me about that. Little Timmy, little Willie, little Willie is no more. So what he found is H2O is H2SO4. So now he's dead. My guess was he was Wait, this is
Okay, everybody ready? Anyone need more time? Okay, now give your eyes up this way, everybody. If you don't have the right charge, it's not the right answer. Okay, so you've got to make sure you have the right charge. Okay, all right, you should have HS minus. Should have PH3 no charge.
Let's go! Wait,
And then CO3 2 minus.
Yes.
Whoa, I got that one too.
Questions on those? Okay, checking these ones. HSO4 minus. H3O plus.
Yes.
And H2CO3.
Let's go!
So that's up to 6 if you got them all right. Any questions on conjugates?
No.
Not too bad?
I need 7 more, and then I'll have 4.
7 more?
Yeah, I can do it. I'll just have to ask great questions.
That's true, that's true. Okay.
What is this?
Let's get this set up. All right, so the last thing we're going to talk about in introducing you to acids and bases
I mean 100.
is a lab technique that we use primarily with acids and bases, but it can be used outside of that as well. This lab technique is known as a titration. Titrations are used to determine the concentration of an unknown substance. So it is a way to know, let's say, for our example's sake, I found this bottle in the lab. I know it's hydrochloric acid, but somebody forgot to label its concentration, meaning it could be anywhere from 0.0001 up to like 12,
That would be bad.
right? So titration is a technique you can use to identify the concentration, meaning how much is floating around in there. Okay? I'm going to have you do a little, well, let's fill this in and then we'll flip the page. The significance of the titration, what we're trying to get to is we're getting to what is known as the equivalence point. The equivalence point is a point at which all of the substance has reacted. By knowing how much has reacted, we can then use stoichiometry to work back to how much we started with. Okay? This is known as the equivalence point. The end point of the titration is the observable change that we'll see with our eyes. And they should be really, really close. The difference is just endpoint has experimental error possibility, right? This is based off the mathematical of what should be perfect. But hopefully they should be fairly similar to each other. You can kind of think of it analogous to like the theoretical yield versus the actual yield a little bit, where this is where we actually saw it change, this is when it should change. But hopefully we get 100% and it's right on the dot. Okay? Here's the basic setup, and once again, we'll do actually 2 titration labs come next term when we do more of the acids and bases. But here's kind of how it's set up. So this right here, this big long tube is known as a burette. The reason why we use them for titration is because they measure a very precise amount of liquid at a time. If you like very controlled, tedious chemistry work, titrations are for you.
Yeah, I'm good.
Okay? Because it is about the tiniest amounts can make or break your experiment. Okay? Turn to really quick, I want you to label something. Turn to the page right here that has a picture of your setup. We'll come back to those graphs here in a second.
Huh?
So turn to the page with this setup. So when you set up a titration, first thing is the known, so you're always trying to find an unknown. But in order to discover an unknown, you have to compare to something you already know. So in terms of an acid-base reaction, if I'm trying to determine an acid, I pick a known base. So what I did is I went into my lab and I got a concentration of 0.1 sodium hydroxide, which is a base. Okay? Make a little note that the burette always holds the known amount. Like, I know its concentration. So it just depends on what you're trying to find. Now, if you're not the tallest of person, you have to use chairs when you do titrations. Because you can't reach the top. Oh, first off, make sure it's closed.
That would help.
Yes. This little valve, if it's vertical, the liquid comes through. Horizontal, it stops. So
That makes
we're good.
sense. Wait. Why is this one washed?
Ah,
Whoa.
Oh, no.
Yeah. It's just deep.
okay.
Yeah.
Made a little mess.
Yeah, so it's not well.
Okay, don't want any spare drops here. Okay, now, let's write that down. So we have, okay, so I have a 0.1 molar of NaOH. I'm trying to find the molarity of my hydrochloric acid. Okay?
Maybe in the initial.
Now, what is significant?
Are we
Go ahead
supposed
and-
to write this down somewhere?
Yes, back. Yep, by where by your picture. Yep, that final page, page 13.
Oh.
Oh,
In the boxes?
Not in the boxes.
Don't write it in the boxes.
Don't write in the
Sarah.
boxes. Those are for something else.
I'll just write it here.
Okay. In the end, if we were to graph our data, which we're not going to get to in this unit, but all titration graphs would look like this, where the titration is measuring the pH versus how much base we add in. So with every drop of base, we see the pH gradually going up because bases have a higher pH. The inflection point, for those that have learned that in math, where it goes from concave up to concave down, is the equivalence point. At this exact point, the moles, make a note of this, the moles of acid equal the moles of the base. That's why we call it equivalence, because they're equal. Or at that point, all of it has reacted with each other. Then if you just continue on, that's why it just keeps growing, is because you just keep adding more base, so the pH just keeps going up. This is the point, normally you just stop it if you're doing it by hand. You'll get these graphs when you use like an electronic reading that just measures that for you, which we'll do that in the lab as well, okay? So I know how much concentration of base I have. So in order, so remind me once again, what's capital M? Molarity. What are the units for molarity? So I need to know a volume to cancel out liters, right, to get to just moles. So I'm going to pick a set amount of acid to use. So let's pour some acid and then I'll tell you how much we measure. All right, we are at 41.9.
Placid, there you go. Placid.
I said that.
this is going in my flask. This is in my burette. And then we're going to start mixing them together. Okay? Now, when you do this, you have to do it slightly more old school. I pulled out my fancy electronic stir to make things easier. Where'd my flask go?
Okay, that was a beautiful picture. How did you draw it?
Wait, who's your what now?
Picture up there, like the flags of the.
Oh, you like that?
It's so good.
It's okay. Okay, so the way this little tray works is this is a little magnet. Okay, I'm putting the magnet in the flask, putting the acid in there as well.
Does the magnet not do anything to the acid?
Nope.
It's a special magnet.
Special magnet, okay? Putting it on here, and then this, if I turn it on,
Wait, what is the point of the magnet?
It's to
We'll stir it.
connect with the stir.
everyone see that?
Spinning so smooth.
So it's an electronic stir. It's what everybody needs on their kitchen stove.
Very quality kitchen.
No, because then when your recipe says stir for 5 minutes, you just turn on your magnet.
Yeah. Oh, that's a good point. Oh,
Right?
yeah, my mom makes caramels and I have to sit there and stir for it.
Yes.
It's so annoying. How much do they cost? Christmas, you know?
No, I want them to build it into my stove.
Yeah, no, that's what I was
Wait,
thinking.
so
Right?
it's just like on the bottom.
You
going
could
down?
actually
Oh.
It wouldn't be hard, right?
Oh, wait, no, it would be really easy.
You're a
Yeah, because there's
genius.
just a
You
magnet
just
under
have a
there.
magnet spinning around.
Oh my gosh.
And then
I
you just toss
know.
it. Well, would you want the magnet in yours? Like,
You just take it out.
You sanitize it.
Yeah, that's true.
You wash
If you keep it clean, put it in, take it out.
Alright.
This is an excellent idea.
I mean, that you would have to be careful that you make sure you remember to take it out, otherwise you're going to get a magnet like in your caramel. But
That would be bad. Yeah.
wouldn't it just, I just always think it was, I need to go on Shark Tank one day with that idea.
Yes.
That's actually like.
I know. If any of you do it, give me some credit, okay?
For what?
This is the back.
I'd like to think.
If you take that idea and run with it, you know.
That's fair. That's fair.
I'll just send you like.
$1.
I'll send you like a list of-
Yeah, we'll send you it. Yeah, definitely.
Okay, so here's what we're gonna start doing. Ready? Oh, so what we're gonna do in those boxes that you didn't draw in yet
Oh my god.
is we're gonna create a molecular view picture of what's happening as the reaction goes. Okay? Honestly, we're gonna talk about the math today, but in this unit for our introduction, I don't care so much that you understand the math as much as what's floating around in there. So think of these boxes as this flask. We're magic school busting into it. What is floating around? Okay? This first one is before I do anything. So we have it set up. Base is here. Acid is here. What's floating around in here?
The magnet.
Just, well, the magnet. Yeah, we're not going to draw the magnet. I mean, if you want to draw the magnet in there, yes, you can.
Okay, I will.
What species is in there? HCl. Okay? Can you see down there if I write this low?
Yeah.
Yeah?
Yes.
Yeah? Okay. So HCl, and it's in water. Right is under the boxes. Now, HCl is an acid, so what do acids do?
They give
Okay.
you
They're great people.
Good.
I
So
get
it's
it.
gonna donate it and make Cl minus and H3O plus.
Can I just write H plus?
So now this is the detail of what's really happening in reaction.
I can't be lazy right now.
No, I'm gonna show you how you can be lazy.
Oh, okay, good.
What you could also write instead though is you can just write HCl breaking apart into H plus and Cl minus.
That's beautiful. That's beautiful.
But
right there.
recognize that this is happening because of the water that's in there. But we're not gonna show the water
because the water's just assumed.
because it's just like part of it. Okay?
Water
Okay,
just
so this is what's happening here before I do anything else. So we just need to draw some H pluses and some Cl minuses hanging out.
It is straight road.
Now it doesn't technically matter how many you draw. I'll draw 3 sets for our ratio. Just whatever you do, you gotta make sure you maintain the same ratio throughout the boxes.
Yeah, if we managed to two of us in there, it'd be like H plus.
Are they labeled like, do molecules like write English letters on them?
Yeah, the entire world is really just alphabet soup.
Oh, that's darn it. Wow, doing wait, so in my stage show would be very complex.
We can magic school us down. We just see a bunch of alphabet soup.
I really hope they don't use comics.
You know how cool that actually
No, it's so
If that's how it really was.
But then true.
Okay, so now, ready? Next step, we're going to drop the base.
That's funny,
Thanks,
because that's
guys.
like, that's like.
I knew somebody would get it. Okay, now,
That took me way too long.
how do I know when I'm done? What are we trying to get to? What point?
The middle where they're equal.
Where they're equal.
No, no.
Well, the problem is, hydrochloric acid is clear, sodium hydroxide is clear. Okay, look at your equation at the top when I mix them. So sodium hydroxide, hydrochloric acid, what are we making?
Salt and water.
We're making salt water. Okay?
Wait,
So-
can you tell me that?
Like, so just tastes like salt water, whereas in theory, that is so weird.
So I'm going to add something here, everybody. Give me your attention.
Freaking ocean.
That will help us visually see that point. Because otherwise we're not going to see the difference of salt water being made, right? Okay, so this right here is an indicator. We'll learn about lots of different indicators to come, but this will help us identify that change. Okay, the point at which all the acid has been used up. Okay, the way this particular indicator works, they're all different, is this one goes from clear to pink when you've crossed that line. Okay, so I'm going to add it to the acid and it will stay clear
What?
if I did it right. Yep, okay.
What?
Last period I did it backwards.
It's a gender reveal, that's what.
Don't actually kind of super cool.
I should find it. With my first daughter, I did a chemistry gender reveal, and I
Yeah.
used this compound.
Hey, let's go, that's so funny.
So now I didn't mean to, but it's kind of cool. Can you guys see the pink right there?
Yeah.
So I accidentally touched this, so it got some indicator on it. So when the indicator touches the base, it's pink. But what's going to happen? So I'm going to start to drop it in.
Whoa.
It's
Okay.
a girl.
Is notice that it's still clear down here. So what we're looking for is we're looking for the point at which it doesn't stay clear. Now here's the meticulous side of titrations, is we don't want it just to turn pink, we want to stop it right when it turns pink.
That's true.
And so it can be
No, it's
different.
not true at all.
That's what she said. He's like, stop it, Devin.
The difference between it is like a single drop. So normally when you do a titration, you set up the flow to not be like a waterfall, but you want it to be just a constant, steady stream, like this.
You prefer waterfalls?
And you watch and you wait.
You know, there's a funniest and verb song about
I was just thinking that. Oh
About
my
what?
gosh, what?
There's a funniest and verb song
Yeah.
all about watching and waiting.
Yeah, it's the
Oh,
one where
really?
Candace in the spinny thing and she's like
Oh.
trying the invisible paint or whatever.
It's a really good episode.
It's a great episode.
That's
Okay.
the songs you like.
Now,
Wow.
the other thing is normally, well, when you do a titration, you have no idea when it's going to change. I obviously set this up beforehand, so I know. So normally you just have to do it really slow. I'm going to fast forward it because I know how long it's going to take. But before we do that, we're just going to let it drip and let's fill in this box of what's going on. So we're starting to drop the base. Okay, so the base is coming into this. Okay. Look at your chemical reaction at the top. What is the base doing as you add it to the acid?
It's just taking the hydrogen.
It's thrown apart.
Good, so bases accept a hydrogen, right? Acids donate their hydrogen. So I'm going to draw it kind of separate but then show you together. So we still have these all in there, right? Okay? So I'm going to draw an H plus and Cl minus. The base comes in as Na plus and OH minus because it separates in the water. The OH pairs up with the H and makes
H2O.
H2O.
Oh my.
Dude, that's magic.
Wait.
Oh my gosh. Taylor,
Now
you're-
technically, the Na could pair up with the Cl, but since it's still in water, they just stay separate. Because what's the one solubility rule you have to memorize or need to memorize?
Salt.
Salt is
And
Na,
potassium.
potassium, and
Sodium.
ammonia,
There you go.
and nitrate.
There you go.
Bananas. Bananas.
Are always dissolvable.
So sodiums are always soluble, so they're always separate. Okay? So I'm going to draw the rest of them as H2O. Let's think. Okay, so we have
There's been several incidents.
another one can pair up with like this guy and make H2O.
Bananas in public.
You have your Na plus and your Cl minus. Now for the ratio though, I'm not to the equivalence point yet. So I don't have equal numbers of both. So I still need some H plus by itself. The equivalence point is a point at which all the H plus gets a buddy. Right now it's not pink yet, so there's still some without a buddy.
They're so sad.
Okay? Questions of what's happening right now as it's dripping?
What is gravity?
Know about this.
No, it's dripping because of gravity. That's why it's so sad.
Oh. Okay, ready to fast forward?
Yes,
Waterfall.
Okay.
Zoom.
Now, as you get closer to the titrate, to the equivalence point, the pink color will start to linger. But we're not there until it stays pink.
Man.
So if you notice, it's starting to get a little brighter. This is how you live on the edge as a scientist. Like going back.
I thought you had to like have a crazy hairdo or something to do that.
No.
Like,
This is how you live dangerously.
Just let it flow.
can anybody do a solid Doofenshmirtz impression?
Dude, I wish.
So notice how the pink like is staying, but then once I turn it off, it goes clear again. So we're still not there yet.
You should go on America's Got Talent and do this. Watch.
Whoa.
Watch as I stop this perfectly.
Or Jimmy Fallon. Jimmy Fallon has chemists and people come
That's
on.
true, he does.
Most of the time they blow stuff up. But
Yeah.
You know, at this time, we can make a waterfall. Yeah, that would be awesome. James Brown.
So it just, this is what's so crazy, once again, between our level, what we see, how many molecules are contained in that tiny drop I'm adding?
I don't want to talk about that.
Like a lot, right? And so that's why it's like so meticulous in that if you go one drop over, you're technically way off of what's equal, right?
Wow.
Stress on
Imagine
the scientist.
Oh, we're so close.
They
Yeah, and
say
then what happens, and hopefully none of you do this, but you might, is sometimes you get so excited that you found it that you turn this too far, and then you burn the whole experiment, have to start over again.
Dude, but imagine if you were doing this and the entire time it was dripping and you weren't using the waterfall to stress. No, that would be kind of miserable.
Yeah, we just sat here for the
Yeah, this is why some college labs are like 5 hours long.
Really?
Because you're literally just staring at something
College.
red.
I don't want to go to college now.
But kidding, some of them are really fun. If you don't, it all depends on what type of labs you like to do. If you like to do very meticulous labs, that's like quantitative chemistry. If you don't want to measure stuff, do organic chemistry, because they don't care about measurements.
I'm gonna do organic chemistry.
Yeah, I'm gonna do
I'll do
organic.
that.
But some people really enjoy like this type of work.
I just love staring at water drip for hours on end.
Oh, we're so close.
So close.
I know it's like that I have.
Oh, it's like slightly pink.
That still looks good.
Whoa, wait.
A drip and a half.
I'm trying to get this song flow.
Oh, dude, okay.
Okay, place your bets. How many more drips do I need?
Oh,
That's
zero.
it.
None.
No more. One more.
No.
Oh,
no.
Is it gonna go quick? Ooh, it's close. Okay, let's draw this way. We'll see if that changes. So at this point,
Two more.
there shouldn't be any more H plus floating around because all the H pluses have gotten buddies. So draw 3 water molecules. What else is floating around? And in a sense, these would be like our spectator ions, right? Because they're just floating around the whole time. So the equivalence point is a point at which the moles are equal and you don't have any more floating around because they've all reacted. Is going to be the magic drop? Now, technically, once you get to the equivalence point, most of the time you're not going to continue onward.
But it's more fun.
Okay? If you have an electronic probe, then those are convenient in the sense you don't have to watch it like this. You just let it drip and the probe measures the constant change for you. So, if we do continue onward and we just keep dropping base in, what's going to be floating around in the flask?
A lot of.
You just asked me, this is how they make napalm?
Good. So pretty much all this, plus,
This doesn't make any sense.
I'm just going to write it like this, excess, Na plus, and OH minus. Right? Because at this point, now the stuff you're adding has nothing to bond with. So you're just going to have extra floating around. Well, I think we might, it looks a little pink to me still. Look a little pink.
Yeah. Dude, that would be magic drop.
I think one more drop.
No.
Really? One more? That's dangerous. You bring the whole building coming down on us.
Just like,
That'd be epic, actually.
Perfect way to die.
okay, any questions on
I want the song low. That's my.
titrations? Now, for the math side of things, once we reached our equivalence point, we can determine how much base we added by seeing how much we dropped in. So we dropped in 41 point
Oh, no, the math.
Now it gets
8.
not good.
Oh, so
They don't do math.
Yeah, they don't do math like Jimmy Fallon.
They don't do
What's
math.
going on?
So we.
Wait a second.
It's like the scene.
So what does that tell me, Winston? What does that tell me?
you need equal parts acid and base.
The ratio is.
You need one
So if I
more.
added the same amount of acid as I did base, what's the concentration of my base?
41.8 milliliters.
That's,
No, 0.1.
there you go.
Hey, what a guy.
So the molarity, since that's the same, those are going to be the same, right? I did a 1-to-1 ratio just to show if it's not 1-to-1 and you can't quite tell, that's where then you can actually use the this equation, which should look
The
familiar.
math app. Look good.
It's like M1V1 equals M2V2, but for acids and bases. Plug this into here, and then you can find your missing molarity. So. Any other questions about titrations? Once again, for now, I just want you to understand what's like the molecular view side, and then we'll do obviously a lot more once again with them when that comes. Good for now?
We should do free practice problems.
I agree completely.
do 3 practice
I'll
problems?
wait with Taylor.
You need 3 more smiley faces?
Wait.
Okay, here's your practice problem.
Fine. I'm gonna get this wrong.
Okay, everyone can have it. It's not just for Taylor.
Yeah.
Okay, I'm gonna write 3 reactions on the board. You need to identify one is acid-base, one is a redox, and one is a precipitation reaction.
That sounds like a lot of work.
Oh, so we
Okay.
don't actually we just have to identify. We don't have to do anything inside.
No, just classify, say that's acid-base, that's redox, that's precipitation.
All right.
Okay?
I just need to.
I got it, Taylor.
Oh, this song is so good. Here, just keep writing.
Yeah. Okay, I gotta think of reactions.
NOH plus We'll never know what that one is. I don't even know if this paper.
What?
Would you include movies or? It was just about general. It was about general. The show was called. And then her mom pulls in and it disappears and she finds out. It's so good.
It must be in the driveway.
Yeah, the driveway is probably
It's
always.
Blueprints starts accidentally put us to switch to all the tomatoes in the driveway.
Exactly.
Okay, there you go.
That was perfect timing. The song just ended.
Wow.
Wow.
That was pretty good, huh? So which one is acid-base, which one is precipitation, and which one is redox? So classify.
Is redox
Redox is like when it has charges and then the charges change.
Kind of. Is that the oil rig one?
Yes.
Okay.
Yes.
Oil rig. Ox is bad.
Wait, so
Is oxygen is leaving?
Wait, what is the next to this NaCl? Is that a
Yes, AQ.
Okay, so the bottom one's pretty easy.
Just guessing the bottom one is. No, you just have to write it as what it is, don't you?
Yeah, but what if we want to write?
Well, then do that, Taylor.
Oh, it's definitely precipitation.
Yeah.
I like this sass.
I get sassy when I'm tired.
Set your pencil down when you're ready to check it.
Okay, let's.
Good process of elimination. That one's at high.
This has like been a constant but very slow fall of snow all day. Yeah. Like it's like we've just been in a snow globe all day long. Yeah.
Wait.
To be determined.
Acid, base, redox. Wow, you were really fast.
I got.
Why are snow
I saw all the kids, I was like, oh,
Why do they always
like,
write
six out, like, so she knows.
you're done to switch things.
I imagine it has something to do with
I know. I don't know. I've never thought about it before.
That was obvious.
It has something to do with like is it how the hydrogen bonds form?
The ballad of Hawthorne.
Because that's like when the freezes, right? Those hydrogen bonds latch. Why is it always 6? Why could a hydrogen bond not
That's
be?
what it was for Halloween. On Halloween.
No.
I'll think about that. Yes, but they're very, very rare.
Wait, there's one of each, right?
Because triangle bonds start bringing the atoms too close, so then you have that problem of where they are pushing away when they're trying to bond with each other. So yeah, triangle bonds, like I can think there's like one molecule chemists have made that does a triangle bond, but it like doesn't really happen in nature that I know of. Because yeah, it's just the the angles are too tight. The bond angles, right, get too tight with a triangle bond. I can't remember what it is, what the chemical is. Yeah. Yeah, there's a lot of hexagons and pentagons for bonds. I see those are like the most, because even squares are pretty rare. Because even a 90-degree bond angle is like pretty tight. But yeah, you get lots of pentagons, lots of hexagons. Oh, it's a liquid. You typically do it's an L in cursive, I think, to differentiate between like the number 1. So, yeah. What does that mean? Okay, everybody ready to check it?
Yeah. Wait, there's one of each, right?
Maybe.
Okay, because I kind of processed it.
Yeah, I should have done 2 of 1. Huh? That would have really tripped you.
I know, I did just process. That would have been really easy.
Okay, this is acid base.
Because there are actually hydrogens in that one. Neither of the other 2 had hydrogen, so it was pretty process elimination there.
Now it's a little trickier because the movement of the hydrogen is a little bit more sneaky, I guess you could say, in that. So first off, number 1, that is a great way. When you're trying to identify acid base, look for hydrogens, right? If there's no hydrogens, it can't be an acid base reaction. The other key thing that often, not always, is made is water. Often gets made in acid base reactions because the H is pairing up with the OH to make water. And then these 2 are pairing up together because they're just both floating around. So this is a redox reaction. How can I identify a redox?
Process of elimination.
Number 1, it's not the easiest one to identify straight up. Minus.
Is it the same as an oxidation reaction?
Yes. Yeah, if you have what's known as like a single replacement, those are always redox. Meaning you have something by itself replacing something else. Those are always redox. There you go. Yep, copper's cutting into the dance.
What a jerk.
Okay.
Go home, copper.
The most detailed way is to track numbers. That's how you know if it's redox or not, is by doing the oxidation states. And then this is obviously precipitation. These are the easiest. I feel like, because you're looking for aqueous turning into a solid. Or, just remember, it could be a liquid or it could be a gas.
We need 4 more smileys.
Did you have a question, Zach? No? Okay. Any other questions? Okay, pull out your smiley face trackers if you want to turn them in.
That's true. I know.